that record up later. So this is what we're supposed to be looking at today. So let's look at it. We're supposed to look at we're supposed to understand that computers are superior over humans in some aspects. Now, how they're superior over humans in some aspects, I would say that has to do with speed, okay? Because we have processors that can do millions, billions, because we're talking about gigahertz. I don't know if you heard this term, hertz, H-E-R-T-Z, hertz. It means a cycle. And so it means a cycle, and actually it's a cycle per time. So we say hertz is cycles per second. So your computers are running at gigahertz. That's billions of cycles per second. So we have a clock in the computer, and that makes the cycle. Every time it does a cycle, there's a number of things happens, and it takes 2 or 3 cycles to actually execute a command. But if you have parallel processors, you can be doing many of these at once. So because of that, I want you to think about that. You've got a machine that can do billions of cycles per second. If you give it a simple task, it can do that simple task fairly quickly. Whereas humans, we can do more complex tasks, we might think, but not at millions or billions of cycles per second. So there is some superiority in computers. I mean, I made a big deal in the previous lesson about the fact that computers compared to humans, there's things that we can do that computers can't. And we've found that in the realms of where we thought we could do things with autonomous vehicles, for example. Autonomous vehicle, one where you just set it off into its environment where it's going to work and it just goes and does stuff. Where we had the example where a autonomous car ran over a cyclist and badly injured him. So there was a problem there with the tuning of the input. So the input into that system, the vision of the car, even though it had multiple sensors all around it, was not able to discern between the difference between a cyclist and some background. So this week, we're going to sort of focus a little more on the fact that, can I ask you guys? So computers can't do anything unless they're instructed to do it. And that's what our job is in this course, is to learn how to do the instructing the computer what to do. And those instructions go right down to the operating system level and right up to very sophisticated input systems. So like, for example, I'm sure some of you have used your telephone and, you just talk to it and give it commands and it does things, phone Muhammad, the phone opens and yeah. So, I mean, people do that. My wife does that. I kind of still do things in an old way because I'm an old guy, I guess. What we want to look at today, and it's not going to be too long, I hope, but what we want to look at today is we want to look at the sort of the basic things. These things have not really changed in computing so much from a point of view of the theory of it for like 50 years. And so we need to look at this idea of a fetch, decode, execute cycle, because this is the way computers work. So I hope you get the idea. Yeah, computers can do things very fast, but they're very constrained. There's a certain number of things they can do, and there's things that they can't do. We have to sort of put our problem into this computer box in a way that the computer can understand, and that's a limited way. And it's based on this idea of the fetch, decode, execute cycle. The decode, execute cycle is there because that's the way the computer is built. The computer is built with a CPU. We'll look a little bit at the CPU, and the way the different parts of the CPU work together makes the fetch, decode, execute cycle. I hope that you've heard of RAM. Yes? Welcome. I hope you've heard of RAM. And you've probably heard of a CPU, right? So actually, when you go to buy a computer, if you're buying one for yourself personally, that's probably the first thing you look at. If you're like me, right, you'll look at it, you'll say, oh, you know, what do I want? I got to have this kind of a CPU, you know, i7 or something like that. Which generation of i7? I want ninth generation i7, and I want it to have this particular speed, and you know, this bus. So there's parts of the CPU that we look at. It's not just the speed of the clock, but also what is the size of the bus on the CPU, and then the bus on the motherboard, and then the memory, the RAM. That's not actually in the CPU, so they're separate. But the CPU also has a little bit of memory in it. So we look at all of that in the design specifications. They will tell us that, and that gives us an idea of how powerful or how fast our computer will be. We will be talking, not today so much. So today we're going to focus on that hardware technology, I guess you could say. And in a lesson after this, we'll talk a little bit more about the precision that's needed in our algorithms. But there's an example that's given here, and we'll come back to it. Suppose I asked you to write for me an algorithm on how to cook an omelet. And you might just say, oh, well, yeah, that's easy. I just break 2 eggs, stir them, then I'll add some spices and some cheese and some vegetables or whatever, and I'll cook them on the side. I mean, different people have different algorithms for cooking omelets. And it sounds pretty easy, right? I mean, especially if you're a cook. If you've been cooking a lot, you know, cooking an omelet, that's no deal, right? But imagine a computer robot trying to do it. You tell a robot to break a couple eggs. Oh yeah, breaks the eggs, crushes them. Oh, well, sorry. Break the eggs so that the shell does not go in the, you know what I mean? Yeah, there's a lot more steps to it than just, you know, to us, it's automatic, right? Because in your mind, you're thinking, well, I don't eat shells. So when it says break the egg, common sense tells me I'm not going to let the shell go in the bowl. But the computer doesn't have common sense. So if you just tell it to break the eggs, you just go like that, break the egg. Okay, now what? You know, you're with me, right? So that's the problem with it. So what seems like a very, very simple thing, get the computer to make an omelet, will probably actually have many, many, many very small, precise steps. Once you get it right, oh my gosh, you're going to have the same omelet every time. So that would be different than the human, because, you know, one day I break the egg, I hit it on this side and I put it like that. One day I do like this. The computer, once it gets the steps, it will do it the same every time. But by the way, that I had before COVID, there was some, and I haven't heard much of this lately, but you'd think COVID would make this happen more. But before COVID, there was some businesses in, I don't know if they're Europe or United States, that they were trying to implement automatic fast foods. So, you know, you'd go there and you'd push some buttons and you'd say, okay, so I want this burger. And you'd be able to say, I want this mixture of meat, because with burgers, you don't have to have all beef. You know, you can mix some beef and lamb and some other meat. You know what I mean? So, you know, I like my burger to taste a little bit better. So I'm going to have beef and lamb mixed, not just beef. And, you know, I want this much fat in the burger and this much cheese. And you could just press some buttons at this automatic thing and it would make a fresh burger for you. Now, to get somebody to do that, that would be a lot of work, but a computer could do that. The idea of this fast food place is that their meat wouldn't even be ground. They'd just be sitting there as fresh meat. As the person comes in, cuts the meat, grinds the meat, mixes it up, perfect proportions, same burger to a specification as required. Right, I'm talking a lot and I'm kind of losing people, I'm sorry. So I'm going to leave that. That's just there. You can read over that. And what I'd get you to do is to please look at that and think on that, because we'll cover that a bit more. So let's go and look briefly. And as I said, it'll be briefly. Let's look at the idea here of a CPU. So we see the CPU in its environment on a computer. So the CPU is delimited here by this boundary. And you see that the beige color represents everything inside the beige color represents the CPU, and the stuff outside the beige color, that represents the rest of the computer, or could be the rest of the world or the universe, I suppose. So the input the input devices, mice, cameras, keyboards. So they are somehow attached to the CPU. They're actually attached to a CPU. All these arrows that go in and out of the CPU and through the CPU, they represent things that we call a bus. And there's more than one bus in the computer. And the buses have different speeds, and they're dependent on the actual distance from the CPU. But the CPU itself has bus. All right, so inside the CPU, there's multiple components. It's not just a single component. You have a control unit. Your control unit is going to include the clock, and it's going to be, how do we go through this process? Now, remember, we're talking about fetch, right? Decode, execute. So we have registers, which is like a very, very localized little piece of memory. So we've got memory in more than one place, all right? And then we have some logic. And so this is going to be where processing is actually going on. You can't really do processing unless you have something to process. And so therefore you have to have your memory. So you got your memory outside. This would be our RAM. Our main memory would call that random access memory. We mentioned that a minute ago at the start, right? But there's also memory inside the computer itself, right? And so there's going to be instructions. As it says, the instructions could come from the main memory. When you type a computer program, say we load a computer program into memory, that's instructions that will come to the control unit, as it says there in the CPU. So this is what I would call Van Neumann's architecture. So Van Neumann, we talked about him in a previous lesson. Do you remember? I'm talking kind of fast, but you guys are okay with this? Because it's stuff that I think you heard before. Am I right? And I'm just revising, I hope. Yes? Yeah. Okay, so Van Neumann, 1950s, 1960s, he came up with this theoretical how we should do our computers. And basically, this is what we've been doing ever since. This is, so when I talk about Van Neumann's architecture, you can think of this diagram. Now, by the way, I put in there some links for you. If you follow that link, we'll follow it and then come back. You can see that this is I think it's a Wikipedia article. No, it's not. It's from Tutorials Point, and it has another way of sort of looking at that, right? So we've got an arithmetic logic unit. Okay, that's in your CPU, right? And then you've got some storage unit. This is all actually in the CPU. So every one of those blue boxes are components of the CPU, and you could map them to the Van Neumann's architecture in the previous diagram. So there's some stuff there. I'm not going to go through and read all that with you, but I'm leaving that with you as something that you can refer to. There you go. I saved you using Google, because you could have found this by Google by yourself, but I saved you 3 keystrokes. All right. Anyways, you got to thank me for that, right? The point that I'm trying to make there is Google's your friend. I'm here to help you, not to sort of be I'm your instructor, but there's a whole world of knowledge that comes from this point. Not just Google. I mean, there's a lot of rubbish that you'll find using a Google command as well. So you have to be sort of careful. You kind of have to know what you're looking for. All right, so here's and I'm not going to go through every one of these things, but I believe this came from, so the above diagram, this diagram came from Wikipedia. You've got a nice resource there, and it's not too big. I mean, you can read through that in a couple, look at that. It's not big, all right? Each one of those things is described there. You got an input unit, all right? Your output unit, storage unit. All of these are actually components of our CPU. And you can have in your own time, just have a look at that. And that refers to these things here. Here we have a lot more detail in that. And so what we see is we see a lot of arrows sort of going. Can you see some points there that look like what I was talking about a minute ago? The fetch, decode, execute, right? So where are we going to fetch from? We're going to fetch from our memory. All right, so coming in there, we're going to have arrows that are coming into the processor, and particularly from any storage units, and that's where we're going to do our fetching. We've got some processing that's going on here. I could say the processing is going on here. Why? Because we have these terms like our AGU and our arithmetic logic unit, our ALU, MMX. These MMX and the AGU, they're components similar to the ALU, but this is all about processing. Okay, and then you see your memory where this data is being stored and then put back into the processor. This is you have memory actually in the processor itself. So I've got another link there. So we got Van Neumann's architecture, fetch code, decode, what we're looking at there. Another link, which may make this a little bit easier to sort of look at. We have memory and we have instructions. Instructions come in. Now, at the CPU level, the instructions are going to be stuff like this. They're going to talk about loading something into a register, which is a very localized small piece of memory in the actual CPU. So we have to make instructions out here somewhere to come to these instructions. So we write computer programs. We have operating systems that work with those computer programs. And we say things like, assign this value to this variable, assign that value to that variable, add the contents of variable 1 and variable 2 together and put them into variables and have variable 3 and then store it. That would then be translated by the operating system to instructions like this. And then these instructions will work with the CPU, and the registers are going to store data in a very short time frame. Again, there's some this is only one page, so I'm not going to go through it all, but there's some things there that will help you to sort of know a little bit about what we're talking about here. So here's those terms that you need to consider in that cycle. Fetch, get the instruction from memory. Decode, internally decode what it has to do. That would be a process of the operating system. Have you guys heard of BIOS? BIOS? Okay, so when the computer turns on, the BIOS is loaded into the random access memory. That is used to do this decoding. And that actually is stored as we call it firmware. That is that we don't have to always write that code. It's actually stored in memory right there beside the CPU. Okay, so that allows the decoding. Then the executing is when the things are going to sort of work them together. And then storing, we put something in memory. So we write a little program, okay? That program has to be decoded, right? And then the decoding of that instruction is going to result in different processors being activated in the CPU. So we've got our AGU, our ALU, our floating points. Floating points is sort of special math. We use that for vector math and that type of thing. You guys are familiar with the concept of a floating point? You can't do mathematics on sort of fractions and vectors. So floating points are used when you are going to have decimal numbers, especially decimal numbers with large numbers of decimals. You need to use a floating point. Okay, you can approximate it with integer calculation by taking one integer and dividing it by another. But if you're going to store the result, you need to have a floating point. So we have special processors just for that. All right, so cache, have you heard of cache? You guys do a computer hardware course? No? Okay. So cache is just very short-term memory. Very short-term, very fast memory that's going to be very close to the CPU. That's what we call cache or cache. Somebody has, who was that? Said, yes, sir. You're welcome. All right, so guys that just came in, can I ask you to grab my, one of you come and grab my thing and sign on so that I don't mark you as absent. Okay. So we mentioned the ALU and the AGU. Could you take it back to the other chaps that haven't signed in also? They can sign in. Appreciate it. Thanks. So we've got the ALU, arithmetic logic unit. It's doing calculations. We've got our floating point logic units. All right. We've got our address generation units, AGU. So we have to have some way of managing where is the data going as it's being processed through this fetch, decode, right, execute cycle. Pipelining is just a sort of a concept that makes that more efficient, because what we can do is we can have more than one thing happening at a time. And yeah, I'm not going to go into that too much. And then actually CISC and RISC is about that as well. And I'm not going to go into that either. But you can see there's not a lot there. I would recommend that as sort of background reading. So let's just summarize what we've sort of talked about today. I'm not expecting you to sort of memorize or draw diagrams like this. This is just to show you that this has been very well thought out. It's an engineering problem that's more or less been solved and is being solved as we speak, right? But there is very specific, very precise instructions and in how to sort of have an efficient CPU. And that's been well thought out. And we've come with this sort of standardized way of developing a CPU, and it looks like this. But it's all about, and you see these words throughout there, decode, prefetch, pre-decode. It's around the concept of fetch, which is we've got an instruction somewhere. It's probably in our memory, our random access memory. We're going to get that instruction. Then we have to try and understand it in a way the computer can understand it, which is only on and off gates, zeros and ones. So we have to decode it. Then we execute it. And probably we're going to have some result that we have to store somewhere. So there's another part to the sequence, right? So in our notes, it says fetch, decode, execute. In the notes in that other link that I gave you, there was another step to store. We probably have to store the results. Have you heard of these things here? DDR memory, common cache? No? Okay. Again, this is not a computer hardware course, though you probably will have to do a computer hardware course as part of your common degree. This is what I want you to focus on. It's a little bit simpler, all right? But you get the idea. What you should have a concept of is there is a CPU into which comes input, your input. And memory is also putting things in and out of the CPU. Then there's output, right? So you should have an idea of all these components: input, memory, output, control unit, which is a clock, then the processor, which contains those things. Where we're going to information very temporarily in the CPU. The CPU has registers, right? Registers. And then your logic. Yeah. So all of these arrows represent buses. There's more than one bus. Okay, so we got bus inside the CPU, and we've got bus between the CPU and each of these things. So there's a bus to the memory, there's a bus to the output, and there's a bus to the input, and there's an internal bus. Now those buses will run at speeds. It's going to be faster and broader inside the CPU itself. The closer you get to the CPU, the faster the bus. This isn't meant to be a computer hardware course. I'm sorry. Don't expect to have lecture after lecture where I'm showing you sort of theoretical sketches of the inside of how a computer works. It's not that. That's not what this is going to be. This is the one and only class on that. All right. So don't worry about that. Don't be blown away about that. But what I do want you to sort of get out of today's lesson is this concept of fetch, right? Decode, execute, and we could add store to that. And how does that relate to this architecture? So we could fetch from the memory, all right, or directly from input. Okay, then we could decode. And so some of the decoding is going to be occurring in here at the processor. The actual execute is going to happen at the processor, and then you're going to do a store, which will probably be in the main memory, or it could go to out. All right, I'm going to stop talking at about that point. I hope that's okay.